Hello everybody and welcome to another episode of Dispar's Lab. Today we're going to do yet another kinetic energy experiment with the same setup. So over here we have the kinetic energy formula. Energy equals 1/2 times the mass times the velocity squared. So I'm going to keep the same mass. This is the mass. I'm going to be dropping this mass onto this pincher. The pincher grabs onto the steel bar with a constant force. And when I raise the ball to a certain height and I release it, then you can see when it drops onto the pincher displaces downwards with a certain amount. And over here with the ruler, we can measure how much the displacement is. So first I'm going to drop it from 5 centimeters high. That is going to be one height. And that's going to be our one velocity. So according to the kinetic energy formula, so it's going to be the same mass throughout every single trial. So the 5 centimeter height is going to be the one velocity. So that's going to be 1/2 times 1, which is the mass, times 1, which is the velocity. That equals 0.5 joules. And then I'm going to double the velocity. Now in order to double the velocity, I have to raise this ball 4 times higher. So to a dropping height of 20 centimeters. And according to this formula, so 1/2 times 1 times 2 squared, that equals 2 joules. And that means that the energy quadruples. So 0.5 times 4 is 2. So when this object travels twice as fast, the energy quadruples, 4 times as much. And then I'm going to raise the ball to make sure that it will fall down with 3 times the velocity. So I'm going to have to raise the ball 9 times as high in order to make sure that it will fall 3 times as fast. So if we insert that number into this formula, then we get 4.5 joules, which means the energy is now 9 times the amount than the one velocity. When the velocity is 3 times as much, the energy becomes 9 times as much. And then I'm going to continue to let the ball drop 4 times as fast. That means I'm going to have to raise the ball 16 times as high. And then the energy will be 8 joules, which means that it will produce 16 times the amount of energy than the one velocity. When something goes 4 times as fast, normally it should produce 16 times the amount of energy. And then one last trial is going to be to let the ball drop 5 times as fast. So I have to raise the ball 25 times as high. And that produces 12.5 joules, which means it's going to produce 25 times the energy than the one velocity. So this is a quadratic increase of energy. So when it goes twice as fast, the energy is 2 squared. When it goes 3 times as fast, it's going to be 3 squared. When it's going 4 times as fast, 4 squared. When it's going 5 times as fast, 5 squared. And so what we're going to see is, hopefully, is that the displacement is going to increase quadratically. That's going to be the energy. The displacement of the pincher is going to show the amount of energy. So we're going to check that out. I have added a little bit of extra mass on top of the ball to make sure that the displacement is going to be bigger, to make it better for you to visualize the displacement. Otherwise, it's only going to be a few millimeters to start with, and it's more interesting to see bigger displacements. It's better to visualize. Okay, so as you can see, the pincher is aligned with the 30 centimeter mark. You can see here 30, it's in red, and when I view it from here, you can see it's aligned with this 30 centimeter mark. That's going to be the 0 line. Now I'm going to raise the ball 5 centimeters higher, so to 35. I think you can see that the bottom of the ball is aligned with 35. Okay, now I'm going to drop it. Okay, the displacement is around 8 millimeters, as you can see. Hopefully, it's 8 millimeters. 5 centimeters trial 2. Once again, around 8 millimeters of displacement. Right, so 5 centimeters, trial 3. Okay, and that's once again around 7 or 8 millimeters. Okay, now we're going to raise the ball 20 centimeters higher, so to 50. There we go, 50. And the displacement is 3.4 centimeters. 20 centimeters, trial 2. 50. And the displacement is 3.5. 20 centimeters, trial 3. And the displacement is 3.2 or 3.1. Now we're going to raise the ball 9 times higher. So 5 times 9 is 45, and therefore 30 plus 45 is 75. I'm going to raise it to 75, like this, okay? And the displacement is 7.7. Yes, 7.7. 45 centimeters, trial 2. It's a little bit dark, but you can see 75. Okay. 7.2. 45 centimeters, trial 3. Sorry, it's really dark. I can't help it. Okay. There we go. 7.5. Right, so now I would like to do 4 times as fast. But unfortunately, the bar is not long enough. I'm going to have to reduce the one velocity with 1 centimeter. So the one height is going to be 4 centimeters instead of 5 centimeters. And then times 16, which is 64. Then the bar is going to be long enough to drop it from 16 times the height. So first, I'm going to do a trial for 4 centimeters as the one height. So 34 now. The displacement is around 0.6 centimeters. 4 centimeters, trial 2. 0.6 centimeters again. 4 centimeters, trial 3. And that is once again around 0.6 centimeters of displacement. Okay, so this time we're going to raise the ball 16 times higher to acquire 4 times the velocity. So 4 times 16 is 64. We're going to have to raise it to 94. Oh, I'm sorry, it's really dark again. You can see the 94 number, I hope. And we're going to drop it. And let's see. The displacement is 10.3, I believe. Around 10.3 centimeters, yes. 64 centimeters, trial 2. Displacement is 10.3 or 10.4. Yep. 64 centimeters, trial 3. I'm sorry, it shouldn't be that dark. Come on. 94. Alright. The displacement is 10.3 or 4. I think it's 10.4. Now I would like to achieve 5 times the velocity. So I'm going to have to raise it 25 times as high. But of course the steel bar is only 1 meter long. And Therefore, the distance that I'm going to have to use for the one height is only going to be 2.5 centimeters. That's going to be the one velocity. And then I can do it times 25, and that will fit onto the top of the bar. So it's going to have to be 2.5 centimeters for the one velocity. So as you can see, it's aligned with the 32.5 centimeter mark. Alright, so the displacement is around 0.4 centimeters. 2.5 centimeters, trial 2. And 0.4 again. 2.5 centimeters, trial 3. And once again around 0.4 centimeters. 0.4. Now 25 times as high, so 2.5 times 25 equals 62.5, so 30 plus 62.5 equals 92.5. 92.5-ish. And the displacement is 10.2, around 10.2. Okay, 25 times the height, trial 2. There we go. And 10.6, 10.6. 25 times the height, trial 3. Sorry, it's dark again. .5. No, it's 10. I think it's 10. Yeah, 10 it is. So now a whole bunch of results. For the one height, the displacement was mostly 0.8 centimeters. So for 4 times the height, we expect a prediction of 0.8 times 4, so which is 3.2. This is a prediction, and the results were between 3.1 and 3.4. So that's perfectly in the middle. That's already success. And then for 9 times the height, we expect a prediction of 0.8 times 9, which is 7.2. And the results were between 0.7.5, between 0.7.2 and 7.7. So a little bit above prediction, but still close. Then for 16 times the height, 4 times the velocity, I had to change the one velocity and the one height to 4 centimeters. That gave us consistent results, a consistent result of 0.6. So then 4 times the velocity, 16 times higher. The prediction is 0.6 times 16, which is 9.6. My results were between 10.3 and 10.4. Now 0.65, so I got around 0.6. It was difficult to see. Maybe it was a half a millimeter more. I don't know. But if it was half a millimeter more, then 0.65 times 16 equals 10.4. And now we're getting close. So yeah, I mean, it's pretty realistic to say that maybe it was half a millimeter more than my eyes could see, you know, but still close to within the predicted range. Okay. Then for 5 times the velocity, the one height was 2.5 centimeters, and that created a displacement of 0.4 centimeters. So the prediction is 0.4 times 25, which is 10 centimeters. My results were between 10 and 10.6 centimeters. So once again, pretty close to the predictions. So as we can see, it is more than significant that the results are very close to the predictions of the kinetic energy formula. E equals 1/2 mv squared. So once again, I think this experiment proves the formula right. There should be no doubt that kinetic energy is a real phenomenon. Physics works.